Good morning. Again, I'm here to talk about the use of GNSS, and in particular, how we assure safety, integrity, and other requirements, specifically for civil aviation, but also for other users. So I'll talk in general about the safety assurance methodology, how we do that in real time, based on bounding range errors, computing protection levels in the precision domain, and relying on a series of integrity monitors to exclude anomalous measurements. This methodology has been developed by many people over the past 20 years, since really the IOC of GPS in 1995. And I'll talk about several lessons that I've learned, and I think we've learned as a community, that make it possible to provide this safety assurance, but also create some challenges. In my case, I've been working on this for about 20 years. I got my PhD at Stanford in 1996, working on risk assessment, both for satellite reliability, satellite design, and working on GPS. In particular, in the past 20 years, we've been working on two different means of augmenting GPS with ground and space-based augmentation, meaning we provide information, we make measurements on the ground and provide corrections to aircraft or other users. In addition, there's a technique called receiver autonomous integrity monitoring that can be used without corrections. I'll talk mostly about this one today. But in the past 20 years, as I mentioned, a common methodology for safety assurance for aviation has been developed. And as I said, that's what I'll talk about today. So to start with, I'll talk about how we define navigation performance for civil aviation. First is accuracy, and that's a standard definition. We simply measure the output of the navigation sensor from truth, if we can measure truth. And we typically represent that by 1 sigma or 95% error. So that, as long as we have a reasonable truth measurement, we can relatively easily measure. Integrity represents the ability of the system to protect the user against hazardous errors. So what we call integrity risk is the probability of an undetected and threatening navigation system problem. So again, the key is, for some reason it goes undetected and it's large enough to be threatening. So that clearly can pose a hazard to the user. Now continuity is a little different. This is the case where there's a failure, it's detected, it causes us to abort an operation. So in this case, we protect, something goes wrong, we detect it, the system tells us, or we detect it, and for example, an aircraft coming into a precision approach at New Orleans Airport has to abort when it's only a few hundred feet off the ground. That's not highly risky, but it poses risks a small risk both for the aircraft and for air traffic control. So we have requirements on continuity. Availability is the fraction of the time that the system meets all of these three requirements at the same time. So we have to meet accuracy, demonstrate that we meet integrity, and meet continuity at the same time. The probability over a long period of time that we meet all three is called availability. Typical requirements for aviation precision approach. For accuracy, we're aiming at a 95 percentile position error on the order of 4 to 20 meters. That's normally not constraining because in order to meet the integrity requirement, we typically automatically meet this requirement. How do we define the integrity requirement? This I'll talk about in more detail. Basically, if we have a position error, an undetected position error that exceeds a certain bound, 10 to 50 meters, and that depends on the operation. For an aircraft approaching to 200 feet above the ground, that number is 10 meters. If it's not coming quite as close to the ground, it might be 50 meters. So if there's a position error exceeding this alert limit without warning, within a time to alert, we call that loss of integrity. and the probability of that event is very small, again, depending on the operation. At the same time, we have allowed probability of loss of continuity, and that's defined per 15 seconds. This probability is somewhat higher because this is not as threatening to safety. The probability that the operation is available depends on the airport and depends on the phase of flight. So for smaller airports, 2 nines is satisfactory. For Chicago O'Hare, they need, because of how busy they are, they probably need an availability of 4 to 5 nines, and that's challenging to meet. They meet that today with several levels of redundancy of the existing instrument landing system. The key to assuring integrity in real time for GNSS is what we call protection levels. And you can think of these as confidence intervals. We establish a confidence interval on the unknown position error that extends out to whatever the loss of integrity probability is. So if it's 10 to the minus 7, we need to provide a confidence interval that's out to that level. And clearly that's challenging. We don't normally provide confidence intervals that large in science. The way this works is the user knows his GNSS satellite geometry, and he needs to apply a range error bound in the range domain to each satellite. And in addition, he has a series of models which represent failures. So combining a range domain error model, his position geometry, so he converts from range to position domain, and a series of fault models, he can determine in real time what his confidence interval or protection level is. And he actually checks that in real time. He updates that every second or every few seconds. Here's a simplified version of the equations for protection level. It starts with, again, a range domain error bound. This equation here, H0, represents nominal conditions. So there's no failure. This sigma needs to bound range errors under nominal conditions out to typically the 10 to the minus 7 level. This is a pseudo-inverse of a geometry matrix that converts range to position domain, in this case vertical position. This is a multiplier that extends the confidence interval from 1 sigma to the 10 to the minus 7, or whatever integrity level is required. Now we have several protection levels that describe a specific fault, and this here is a bias. This bias represents the worst case fault that would go undetected by the system. Now, I mentioned we have monitors in the system that will detect large faults. The largest fault that might go undetected at a certain probability goes into this term, and then this is the remaining probability of nominal error. It's D-weighted, so this number, this 10 to the minus 7 K-factor, this is a smaller K-factor because we're already assuming a failure exists. So in a well-behaved system, usually this is the largest protection level. But we have these protection levels as well to express in real time, the protection level under nominal conditions. Now, there are also faulted conditions without defined protection levels. And in that case, they have to be bounded by either one of the existing protection levels. So as an example, there's a failure mode called satellite signal deformation, where the actual signal, the CA code signal broadcast, is deformed. We don't have a protection level equation for it, so it needs to be bounded by this one. And that implies requirements on the monitoring for signal deformation. Again, this emphasizes the importance of those two sigmas. This is really most of the work goes into establishing what these numbers are, and we have to do that conservatively, as I'll explain later. So here's, again, how safety is defined operationally. Again, you can see accuracy is defined as 95 percentile vertical, and here shown lateral error. The user can compute this, but this is pretty much met automatically as long as the user's meeting, as long as integrity is met. So in practice, the user computes his vertical and lateral or horizontal protection levels, compares them to the alert limits, and these again vary depending on the operation, whether it's en route or Category 1 precision approach. As long as the protection levels stay within the alert limits, we verify integrity in real time. We're saying that the unknown 10 to the minus 7 level error is within what's safe. Now again, that's conceptually simple, very difficult to do in practice. Not very difficult, but it requires a lot of conservatism, and that's really one of the lessons of this talk. So with that in mind, what does the user actually do? So think of the user as an aircraft, although it could be a train or a boat or a car potentially doing driverless operations. So the user is making GNSS measurements, typically once or twice a second, if not more often. The user is doing his own integrity monitoring because there are faults that could occur that are just local to him. For example, local multipath or local RF interference. And if his integrity monitoring detects a fault, he will exclude satellites, remove them from the geometry, and then later bring them back in once the fault is gone. If the user is applying corrections either from space-based augmentation or ground-based augmentation, he'll receive a separate correction message and incorporate that. He'll actually apply corrections to his measurements. These corrections may tell him that the ground has detected a fault. Even if he hasn't detected it, the ground may have detected it sooner, and this will tell him to exclude that satellite. So there's actually another potential exclusion and recovery loop right in here. So what he has here is a corrected and verified set of measurements with range domain error sigmas for each satellite. Now he can compute his protection level and compare that protection level to the alert limit for his operation. If the protection levels, they're vertical, lateral, and horizontal, if they're all within the alert limits, we verified that integrity and accuracy are met, and implicitly continuity is met. That's verified offline. So we just continue operation. If that's not the case, the user has the option of trying to reduce his protection level by additional satellite exclusion. But eventually, if he's not able to meet this constraint, his integrity is not verified and he aborts his operation. So in this case, we've protected integrity at the cost of loss of continuity. Now keep in mind what this is saying. This is not saying there's a present hazard. This is saying we cannot validate at the moment that we meet the integrity requirements of the required probability. So most of the cases where this occurs, there is no hazard, no immediate hazard. But this is the cost of the requirement to validate integrity in real time requires us to demonstrate this in real time, and sometimes we will lose continuity even when nothing is wrong, simply because of the need to assure this all the time. I'll talk a little bit about integrity monitor design. Most integrity monitors were designed to target specific faults or anomalies, and I'll show you what some of those faults look like. However, what makes the process of design complex is that monitors will respond to multiple faults. So here's a simple example. We use the GPS carrier phase to detect satellite clock failures. But when the satellite clock runs off, we'll see that in the trend of carrier phase. It will vary from natural extrapolation. However, other faults can cause the same thing. A cycle slip could cause that. RFI could cause that monitor to flag. So we have to have a separate set of monitoring to resolve the potential for multiple monitors flagging on the same fault. This is simple detection theory. Each monitor has a test statistic multiplied by a certain a K-factor based on the allowed probability of false exclusion, false alarms under nominal conditions. That establishes a detection threshold. And if that threshold's violated for any monitor, then we remove the affected measurement. And as I said here, then we have to try to resolve what caused the fault. However, in order to generate this and verify that this protection covers the fault that was targeted, we need what are called threat models. A threat model is a specific deterministic description of every type of anomaly. So I mentioned signal deformation. It's something that occurs very rarely, but we developed a model that says if signal deformation occurs, it will occur within this general form and with a bounded set of parameters. So given this model of an anomaly, then we can verify that our monitors and our protection levels provide the necessary integrity protection. So these anomalies occur rarely, so we rely on a combination of theory and whatever data we have to produce a threat model. And what we're saying with a bounded threat model is we can't guarantee that a fault will always stay within the bounds, but if a fault outside the bounds the probability has to be smaller than the integrity requirement. Once we have this model, then we can, using a deterministic simulation, we can determine what is the worst case impact. And in the case of aviation, what I call specific risk, we have to protect not only the average of all points in the threat model, but the very worst point. The worst point is not necessarily the one that causes the largest error. The worst point is the one that's is the hardest to detect. It's just large enough the error is just large enough to be hazardous, but small enough to be hard to detect. I'll give you an example. In the case of an ephemeris failure, very large ephemeris failures are very easy to detect. But there's a range of ephemeris failures that are just large enough to be hazardous, but small enough that we're not guaranteed to detect them. And that becomes the worst case user impact. That's what actually dictates the protection level. So that's a change of perspective from what you might think. Again, the key is we're not averaging, we're not considering all points and taking the average risk. We have to cover every single point and meet the integrity requirement at each one. Now briefly, because I'll be talking about threats related to GBAS, ground-based augmentation, I'll just talk briefly about what ground-based augmentation is. At an individual airport, we cite 4 or more reference stations at known locations so we can measure and estimate the errors in each GPS satellite. So we estimate the errors, do our own monitoring and using those integrity monitors, exclude faulted measurements, send up corrections for the remaining measurements and those range domain error bounds using a VDB. So this is VDB that's in the VHF ILS localizer band. So aircraft already have antennas to receive these corrections. And again, as I showed you before, they apply the corrections to their measurements, remove any measurements that the ground is excluded, and compute both their position fixes and their protection levels, and assure integrity in the method I showed before. And the key is providing these corrections gives us accuracy on the level of less than a meter that allows us to meet the accuracy requirements for even Cat 3 precision approach. Verifying the integrity is the biggest challenge. So this is just a very brief sketch of how we assure integrity, both in real time and offline. Now I'll talk about what we've learned over the many years working on this. In the early years of GPS, satellite anomalies occurred occasionally, relatively rarely, but occasionally. We had enough examples, for example, to understand certain fault modes, particularly satellite clock failures, and build threat models for them. However, they were still fairly rare. We were given a fault probability that was met, and so we could use this in our integrity justification. Since 2007-2008, when the master control segment was updated, these anomalies have become rarer. In particular, GPS clock failures have become rarer. This was mentioned in the talk yesterday about the history of spaceborne clocks. Failures that before 2007, there were quite, this probability was dominated by satellite clock failures. Now they're much rarer, and so it's quite rare to see any kind of anomaly that's not immediately alerted to you. At the same time, nominal user range error in GPS has steadily decreased. So today, most of you use GPS in one manner or another, and you're getting a huge benefit from the improved performance of GPS without knowing it. Or you may know it, but whether you do or not, it makes GPS incredibly capable. This is a kind of an illustration from the GPS program office of the improvements since 2001 in RMS user range errors across all satellites, decreasing steadily. It had already decreased substantially from IOC. And you can see how it decreased significantly down to 1 meter by 2007. And again, this is when the OCS update occurred. Since then, the system's been relatively mature, and this further improvement just comes mostly from retiring old satellites. So you can see, since 2008, you can see the difference between typical satellites and the oldest satellites remaining. So as these satellites get retired, and in fact all of the Block 2As have been retired, this number slowly gets better. And this is really tremendous, really tremendously low URE for the civil signal without corrections. Much better than we would have anticipated back when we started 20 years ago. This plot is the work of many years of analysis of collected GPS data, looking specifically at measured user range error divided by the URA that's broadcast in the navigation message. So this is normalized, and it's a 1 minus CDF probability plot. You can see the red curve is the Gaussian based on the broadcast URA. You can see how much better the actual performance is relative to that Gaussian curve. One reason is that the minimum URA is 2.4 meters, and typical performance, as I showed you, is much better than 2.4 meters 1 sigma. In here, you can see accuracy is very, very good, but as we get down to probabilities of 10 to the minus 4 to 10 to the minus 5, we have non-Gaussian tails. And as we cross 10 to the minus 5, we're still bounded by the red line, the Gaussian, but when we get below that we begin to violate that. And we see this not only with GPS data, but with our augmented data as well. This is typical behavior if you have enough data. That very good data down to 10 to the minus 3, then once you get down to 10 to the minus 4, 10 to the minus 5, the tails begin to spread out like that. And I'll talk a little bit about that, why that is later. Now this, from the same collection of data, since 2008, it shows two key things. One is the green for each satellite this is kind of going from older satellites to newer satellites. You can see it's a summary of each satellite's history, where green represents healthy and valid data. Little blue and red dots indicate the satellite being unhealthy and telling you it's unhealthy. The satellite tells you it's unhealthy by broadcasting an unhealthy flag in the navigation data, or it may suddenly switch to non-standard code, which you're not supposed to track. It can also do what's called a sat zap. There are various ways for the satellite to tell you it's unhealthy. What's circled here are what are called service failures. 5 cases where the satellite exceeded 4.42 times the URA without any alert from the system. And compared to the past, only 5 of these in 8 years is a much lower probability than there was in the past. Only 1 at a time. And the mean time to notify when these occurred was only 21 minutes, compared to what's a guaranteed response time of 6 hours. So, just to clarify, These are ones we've observed. They're not necessarily all that have occurred. And it's possible for a fault to be hazardous for GBAS that isn't a service failure. Signal deformation is an example of something that could cause that. But in most cases, if it's hazardous for GBAS, it would show up as a service failure. So again, the lesson here, this is really tremendously good performance and better than would have ever been expected for the civil system. Better than was promised at FOC, and better than is currently mandated in the SPS signal specification, or performance standard. So again, GPS sets a high standard, and what we have to be careful of is assuming that other new GNSS constellations, like Galileo or the rejuvenated GLONASS constellation, have the same performance. Because again, as I mentioned, this wasn't achieved overnight. This starts in 2008. It's always been good, but it certainly wasn't this good back in 1995 or 2001. So with systems that are new or rejuvenated, we can't make the same assumption. We can't simply assume that this performance will be satisfied by other constellations. And here's an example for GLONASS. This is a failure that occurred in April, actually on April 1st, 2014, on April Fool's Day. And what happened here, it was an Ephemeris failure, meaning bad Ephemeris data went into the GLONASS update the GLONASS navigation data. What you can see is that many different satellites were affected at the same time. So certain techniques like RAIN that rely on redundancy would not be able to detect this kind of fault. Many satellites, again, they got a faulty upload at the same time. They all had, or many had hazardous errors on the order of hundreds of meters of range error, but they all appeared to be healthy to users. So this is an example. This has not happened for GPS, not on multiple satellites. But this is the kind of thing that has happened on GLONASS, and it happens more often on GLONASS. This is a caution, again, new constellations or constellations like GLONASS that kind of most of the satellites faulted and then were rejuvenated with new satellites. They need time to build up the kind of history that we can rely on as we have with GPS. So, GPS performance is wonderful, therefore GPS anomalies are rare. They're not so rare that we can neglect them. They still occur more often than our integrity requirement. They occur more often. Their probability is higher than 10 to the minus 7 per approach. So we still have to demonstrate that we protect against all of the anomalies that we can foresee that have occurred. Many different types can be considered, and very few occur more than once or twice. So it's difficult to build a threat model that we're confident bounds all possible faults. And this is a real challenge. I'll show you some examples of faults and how we've dealt with them. As I mentioned, clock failures still occur. The clock failure is mostly the atomic frequency standard just running off. The frequency runs off. This happened much more before 2007. Here's a particularly severe occurrence back in July of 2001. This is plotted as drift rate, meters per second versus time. And at the initial transient, this is where our monitor would detect. So it's at least the GBAS monitor would detect. But a standalone user with RAIN might not detect right away. But this behavior is very severe. This large acceleration, then this unusual back and forth, that basically it needed to be detected and alerted, and the OCS detected it, sent up an upload to make the satellite unhealthy in about an hour and a half. What's a more typical clock failure isn't quite as severe. This one was in 2003. Here we're not plotting drift rate, but just error, user range error versus time. And this is over 20 hours. So here the satellite was generating significant errors. Instead of flagging it as unhealthy, the OCS simply uploaded the satellite with new clock correction parameters. You can see, and kept it healthy, so you can see the error went down. Then the unusual behavior recurred, another upload. keeping it healthy. Finally, the unusual behavior got bad enough that an upload occurred to make it unhealthy. And in this case, what's typical in these cases, they'll spend several days trying to resolve the anomaly before bringing it back to healthy. So again, this behavior, this kind of transient, particularly this kind, we'll detect right away in an augmented system, but not necessarily in an unaugmented system. So I'll talk a little bit about ephemeris faults. Again, these were considered to be very rare back when we built the original threat model, because we knew clock failures were much more frequent. Now clock failures are infrequent, and at least two examples of ephemeris failures have occurred in the last 10 years. Still rare, but not rare enough that we can ignore them. So just to be clear, an ephemeris failure is when the navigation data representing the GPS or GNSS satellite orbit gives you a satellite location that's significantly in error from where the satellite really is. And it has to be significantly in error to create a hazardous error. In this shows the organization of the threat model. We divided this threat into two types. One is type B, where the error occurs just due to a erroneous data upload. The satellite is still in the same orbit, didn't move other than normally, but for some reason, faulty data was uploaded. At one moment, the data is good. After an update of the navigation data, suddenly it becomes bad. This is relatively easy to monitor for because we can monitor the consistency of the data. This one is harder to monitor for because it involves an actual satellite maneuver. The satellites are maneuvered on average once a year just to adjust their orbit, to keep them in the proper orbit slot. And here the concern is that there are several concerns, but the concern is an error is made related to the maneuver. I'll show you one possibility, the simplest one, but either during the maneuver or after the maneuver, the uploaded ephemeris is incorrect. Again, we thought both of these were rare. This one would be more likely. We saw a type A threat in 2007. So what happened here? The satellite was maneuvered. You can see the satellite being maneuvered based on range error in red at Honolulu and position error at several locations. If you look at the red, which is this one, the satellite, its error is small. We know that this increase in error occurred as the satellite began to be maneuvered. Okay, again, it's a planned maneuver. Maneuvers are normal. A NANU was released ahead of time saying that the satellite would be maneuvered. Only one thing went wrong. The satellite was still flagged healthy. A mistake was made in the ground system. They forgot to upload an unhealthy flag before they began the maneuver. So these are actual errors that uncorrected users would have experienced and did experience until the satellite was flagged unhealthy. So this is a test case, a simple test case of a type A failure. And we don't rely on just this case occurring. The threat model for type A includes all sorts of different possibilities, some of which are much harder to detect than this one. More recently, a type B failure occurred. And you can see here, in this case, at a particular ephemeris changeover on a particular satellite, a very large cross-track error occurred. Now, normally the errors are very close to zero, but after a particular upload and a particular update, suddenly, the satellite hasn't moved, but suddenly good data is replaced by bad data, giving an error of over 1,500 meters cross-track and a few hundred meters along track. What happened here is that something normal a normal update procedure was messed up. The Earth, inside the navigation data are what are called Earth orbit parameters. They relate the satellite orbit, kind of in inertial space, to the location of Earth. That way we can connect where the satellite is to a specific location on the Earth's surface. Those are updated occasionally the updates are tiny because the Earth orbit parameters change very slowly over time for physical reasons. For some reason, the data in the update was faulted. So the update was made, but the data passed to OCS was in error. They put that data into satellites, into the filter that generates the navigation data. This was the first satellite that happened to be uploaded. So this satellite was uploaded, and clearly when we look, and the error was immediately evident. So in this case, if this hadn't been detected, this error would have been uploaded one satellite after another. Pretty soon we would have had several satellites impacted. But fortunately, OCS saw this large error right away, detected excluded this satellite, and then prevented and corrected the problem before any other uploads occurred. So unlike the GLONASS case, where many satellites were uploaded at once, they all had the same error, the same cause of error. We had an error that could have affected all satellites, but because the satellites were uploaded one at a time, it only affected one, and only for a relatively short period. Now the last fault I'll talk about is not based on GNSS, but based on the atmosphere. Typically, the ionosphere, signals transit through the ionosphere, and there are various things the ionosphere can do. It delays the code phase, advances the carrier phase, and we can correct that using dual frequency, which is what future RAIN users will do. But in SBAS and GBAS, we have single frequency users that either apply corrections or they assume that the ionosphere is very steady. Whether it's high delay in red or low delay in blue, it's very steady over the 10 to 15 kilometers between the reference station and the user. That's true almost all the time. This is the exception. This particular day, which occurred shortly after a large coronal mass ejection from the sun, what you can see here again is a region of very high delay with very low delay surrounding it. So our concern for SBAS and GBAS is the gradient between high and low delay. If it's possible to have an aircraft in the high delay region and the ground in the low delay region, we can have a significant differential error. Now we've studied this problem for several years. I've become a quote-unquote ionospheric expert without any space physics background, trying to understand this problem and bound not to fully understand the physics, because we can't, but to bound its effect on on GNSS. We built a threat model based on all the observations we could make in CONUS. Many of these are from that event on November 20th, but there's several other events in here. Observed from data, validated, and then plotted this way. And this forms kind of a threat model showing the maximum gradient. This is really parts in 10 to the minus 6 versus satellite elevation angle. And we also we built a geometric model expressing the speed of motion, width, and total delay. So we apply not these points in here, but the bounding gradients. We simulate that in GBAS, and that tells us the maximum error. It turns out that this threat has a bigger impact on GBAS integrity than any of the satellite threats that I mentioned. And so this is actually what dominates our final integrity, the final protection level. Just briefly, as I'm running out of time, the real where all this leads to is a great deal of conservatism. We need to build threat models that are deterministic, but we don't really know the bounds of what can occur. So we need to assess everything very conservatively. We need to protect integrity, and we need to make very conservative assessments. On the other hand, every time we protect integrity, we're losing continuity. It's very difficult to meet both simultaneously. And there's a further complication, which you would not expect unless you've worked in the FAA for a long time. The FAA assesses probability of faults using, again, what we call specific risk. In specific risk, we don't just take the probabilities and convolve them together, the normal way we would do probabilistic risk assessment. In specific risk, we have to separate out faults that could have been foreseen, like for a system, a clairvoyant system that can see GPS beyond what our system can see, and treat those as known events with a probability of 1. So that means the normal way you would calculate probabilities we can't use, or the probabilities we have to use become much more conservative. And again, this comes from the way aviation safety has evolved. This is a translation of really a deterministic way of evaluating safety, and it just generates a much more conservative assessment. It doesn't necessarily apply to non-aviation, but it makes aviation particularly difficult. The bottom line is we need to be very conservative, in particular in assessing probabilities, creating fault models, and bounding range errors in the tails. The key is we use Gaussian distributions in the protection levels. The actual data is non-Gaussian for various reasons. The Gaussian distribution we use to represent non-Gaussian data has to be very conservative, and therefore performance is lost. If we go back to this slide, as I mentioned before, this is very good performance over a long period of time relative to the broadcast sigma, but that broadcast sigma only bounds down to 10 to the minus 5. So when we control the broadcast sigma, like we do in augmentation systems, we will need additional inflation. This red curve will have to shift way out here to protect integrity, to create protection levels that we know are safe. As a result, we lose performance. What was it? Okay. This shows real quickly an example from SBAS where over a 3-month period, the maximum error was 7 meters in vertical. You can see that protection levels varying from 10 to 50 meters. I'll skip that. So we have, just briefly, we have a common methodology to assure safety for civil aviation, and it's adaptable to other systems, keeping in mind that it really is specific to the FAA approach and should be modified, particularly the specific risks. Fortunately, GNSS, particularly GPS behavior, has relatively few anomalies. It's difficult to assure that the threat models cover all possible anomalies. So we have to be conservative in creating these threat models. The safety standards create, by definition, a difficult trade-off between integrity and continuity. And bottom line is, we are experts in conservatism. And also because we work in a consensus format, typically the most conservative, most pessimistic person tends to determine the amount of conservatism applied at the end. So I hope that gives you some background on how we protect integrity in GNSS. I hope there's time for questions. Thank you.